Topic 15-4 is applications of regressions. I apologize in advance if this looks to be a jagged video. I'm trying to go back and forth between using Desmos and showing you what I'm doing on the paper. So if you actually have the paper printed out and you can follow along, that's great. If not, I'm going to try to be specific so you don't have to pay attention to what's in this corner down here. And I'm got the notes printed out. So it says most data collected in real world situations does not model perfect linear, quadratic, exponential relationships. That's true. All the relationships, the world's not perfect. The data is not perfect. Though it will not always be perfect, regression fit and the calculator can't find the line of best fit. They can find those messy real world situations. And remember that we want R squared equals 1. That's a perfect fit. The closer to 1, the better the fit. So, example, we're doing a panda example, and it's going to refer to another worksheet, but we haven't done the other worksheet. They rearranged some worksheets, and this will sit by itself. The table shows the relationship between the weight of the panda and its age. So, I'm going to just think about an animal or a human or something being born and the weight gain, and whether that's going to be linear, like I gain the same amount every year, whether it goes in an exponential growth curve, or whether it goes in a quadratic curve. And so we're going to use this panda. I'm going to doubt that it's going to be linear, because that means every year that you would gain, but pretty much you start to taper off, okay? And you don't have, okay, so you don't gain the same every year. You do start here and go, the dots are way far, but in exponential, the points keep getting wider apart. But in quadratics, they're going up, and they go up and they have a second difference. And so my guess is it's going to be a quadratic. Okay? So that's my guess. Not linear, not exponential, because exponential, as it grows, the dots get farther and farther apart. We saw that with the infections of the coronavirus. Okay, so what I'm going to do is I'm going to do the table. And so I'm going to add the table. And 1, oh, I ended up doing 11. Sorry. 1, 2, 3, 4. 6, 8, and 10. I'm just putting in the data. I put all my X's in first because I can just put enter. 10.5, 7.6, 12.5, 17.1, 24.3, 37.9, and 49.2. Okay, so we are going to come down and we are going to y1 equals tilde, not y1 tilde, that replaces it. That means the tilde is the regression, mx x1 plus b. And I look, and my linear regression R squared is 0.99. Okay. Then I'm going to do the next one. Y1 regression AX squared plus BX plus C. And then for every x, I need to come back here and put my 1s. And that's 9964. That's way closer. And then I'm going to do y1 equal regression a, b, x, a, b to the x1. And that is 0.96. So between the three of them, this has the highest. So I am going to use the coefficients, and I'm going to use it to the hundreds. So this would be .12x squared plus 3.7x minus 0.6. So what I'm going to do is I'm going to now create an equation and say y equals 0.13, because I'm going to round to the nearest hundreds, x squared plus 3.71 x minus 0.6. And I'm going to turn off these other equations. So I have my my quadratic regression to mimic the age and weight of a panda. And now it says use the equation to determine the approximate weight of a 7-month panda. And so I'm going to add a table. Actually, I'm going to add a table. And so now that I have my equation, I'm going to, there we go. I'm going to go in here and I'm going to substitute 7. So 0.13 times 7 squared plus 3.71 times 7 minus 0.6, and that gives me 31.74. And then this is from a different, when the notes were in a different order. Okay, example 2. The table shows the average tuition. Actually, I'm going to stop the video there and do example 2 on another video.